Well, thanks everybody for getting up on a Sunday morning. I'm very impressed. I'm very happy to be here. This is my first PyData, and I think it's really a vibrant community. It's really great to be here. And so thanks a lot to the organizers, I think especially Ian, for setting up the meeting and inviting me. So I put up this title, and now I look up at it, and I have to live up with the promise I gave you. So that's kind of a challenge. Just a disclaimer, this talk is as much about people and project as it's about code and algorithm. It's not only a technical talk. So to set the problem, I did a PhD in quantum physics. Nothing related to algorithms or machine learning. It was more about vacuum systems, which means leaks, electronics, which means shorts, and lasers, which means injecting fibers, horrible things. It was actually great training for agile-like project management because you've got short cycles and things fail. So computers were part of the game, but there were only one part of the game. And the kind of things that we were doing was coding in MATLAB and C, and eventually Python at the end, and mostly experimental control software and data processing. And the reason I'm mentioning this is that it really shaped my vision about computing and software as a tool that is there to serve a purpose. It's not an end by itself. So if we fast forward to 2011, I kind of switched gears in the meantime, and I was recruited as a tenured researcher in computer science at INRIA, which is the French computer science research. And that was a huge deal for me because, I really look up to INRIA. I think it's a great institution. It does a combination of really basic fundamental research in computer science and great applications and great software. So that's really the place where I wanted to be. And nowadays, I have a growing team that focuses on some applications of data sciences. And I'm really happy to say that we're starting to be recruiting pretty good people. And for instance, our last recruitment was Olivier Grisel, whom you might know. So we're starting to have a pretty solid team. So that's really great. So what do? I'm interested in using machine learning kind of methods to understand brain function. So I'm going to give a bit more details, but the idea is that we're going to try to link basic things. Oh, yeah, that's not going to work. That's going to work. We're going to try to link basic neural activity to cognition and thought. So that's very ill-defined, and that's the general setting. The way we're going to do this is that we're going to use functional MRI. So functional MRI uses a standard scanner like you have in every single hospital, and it records the brain activity of a subject. Time-resolved, spatially resolved brain activity of a subject. So you get a movie of the brain activity of the subject.
Sorry, can I just move your mic?
Sure.
It keeps attacking on the
OK.
Yeah. There you go.
Thank you. So yeah, that's the data we work with. And our big goal is that of what's known as cognitive neuroimaging. And the idea is that we want to learn a bilateral link between brain activity, as we see it in functional imaging, and cognitive function, where cognitive function is an ill-defined concept. And we can tackle this with machine learning. And one problem that we can write as a machine learning problem is what's known as encoding models. So the idea is that you're going to start from a description of the stimuli, and you're going to try to predict the neural response, so the brain activity. So that's a machine learning problem that I can solve. It's interesting because it gives us a window into the brain representation of the stimuli. So a good model that is able to predict well the stimuli probably has a good description of the external world. So you can see it as feature engineering a description of the world that matches our brain. Another problem that we can do is what's known as decoding. So decoding is the inverse problem. you're starting to predict, you're trying to predict the stimuli from the brain activity. So it's a brain reading-like problem. It always gets, great traction in the newspapers. You see, oh, people were able to decode dreams. So what this really is a data processing challenge. And so, for instance, if we take visual stimuli in 2008, there was a Japanese group who was able to show some pretty impressive stuff where they would do visual image reconstruction from the activity in the human visual cortex. So they would look at the human visual cortex, and they would be able to predict somewhat what people saw. So that was a feat. It was a tour de force. The problem is I don't think science should be tour de force. I think it should be reproducible, and this is a citation by Victoria Stoughton, who's big on reproducible science, and she says that it needs to be open and verifiable by others. So the way I put it is that this is software, this is data processing. So software, we want to make it work first, make it right second, and then I want to make it boring. It's when something works really out of the box, when it's routine, then you forget about it and it's boring. And I want, things like visual image reconstruction to be boring. So we're getting there. You've got a code example on the web that you can download. The slides are going to be on the web. I'm going to put them on SlideShare. So you can download it, and you can run it, and it's going to fetch the data from this experiment, and it's going to run classifiers, and it's going to produce images like this. So this is the stimuli that was presented to the subject. This is what we reconstructed, and this is the binarized version. So this you can run. So this is our goal. We want the code, the data to be available, and things to just work out of the box. So this is a new project that I'm starting to invest in, that we've started in our group that we call NeuLearn, for Neuroimaging Learn. And this is a software development challenge. We're taking a science problem, a paper, and we want this to be completely reproducible, make you happy. You can use it on new data. All right, that's software. Once this works, well, we can do new things. And if we're able to do data processing as a routine, then we can throw in more data. So then we're going into the direction of big data, so super trendy stuff. Why we're interested in this is because we're going to be able to learn richer models of brain function. Not only visual image reconstruction, but detecting the type of object or the emotion, all this in one model. So that's super challenging, but I'm very excited about this because what we're getting at is accumulation of scientific knowledge. So basically all those experiments to learn formal representations of this knowledge. So the predictive model works not on concepts, but on representations of these concepts. And so I think this is really exciting because I think we're getting at the core of what science is. And this is a citation by Stephen Hawking. And he says that a good theory must accurately describe large classes of observations and make definite predictions about the results of future observations. Okay, that's machine learning. I've got, train error, test error. So what I'm getting at is I think we're going to be facing more and more of this, which is data-driven science, and it's not only about minimizing an error. It's about understanding things and using machine learning. And I think that's super exciting because this is the future. And so that's the reason I'm in the business of cognitive neuroimaging, because I think those new tools, not tomorrow, but in 10 years, will be shaping what we do in cognitive neuroimaging. Problem is, on a day-to-day basis, I'm bothered by minor details like the fact that we have buggy code or slow code, or that my main data scientist might leave, or that I've got new interns to train, or actually that I don't understand the code that I've written a year ago. So, in a way, a lab is not much different from any other startup or technical endeavor. You have difficulties and you have risks. Difficulties are recruiting. You all know it's really hard to recruit good people. The fact that you've got limited resources, whether it's people or hardware, and the risks. Well, I want to point out two really important risks that we're all facing. One is the bus factor. So the bus factor is how many people it takes to be hit by a bus for your project to stop. That's really important. Many, many labs or startups or software projects have a bus factor of 1. If one critical person disappears, that thing stops. And actually, I think that this is like a sick joke. But I think it took another stance 2 years ago when we lost John Hunter. So John Hunter was the creator of Matplotlib. And so he died 2 years ago of cancer. It was very quick. We lost him really quickly. And it was a big hit on all of us because he was a friend. And so that's the sad part. The great part is, Matplotlib is a striving project, even without John, because he built it right. So we joke about these things, but if you want your projects, whether they're a startup, whether they're a software project, to survive you because you've got kids and you move on in life, you need to think about these things. Another really important problem is that of technical debt. So technical debt is, say I code my project, I build my startup really, really fast. I don't worry about, getting the code right, getting the minor details right. Well, at some point, this is going to catch up with me. It's just like my car. If I don't do the maintenance of my car, it's going to fail at some point. And I'm going to have to buy a new car or change the engine. That's a big risk, and people keep falling in it. So I think these are the two risks I'm most worried about. So if we go back to my mission as an academic, I need to revolutionize brain data processing. This is what I'm here to do. But I actually have, a very tight budget, funding and science, blah, blah, blah. And I'm quite aware of the problems. So let's try to take a step back and think about what kind of patterns I see in our data processing. First, let's try to look at our workflow. Our workflow is mostly interact a bit with data, write a script to do this interaction, and then hopefully turn this into a module with a set of functions that are useful. Once I've got this module, well, I can apply it to new data or the old data, and I can keep going. So there's this iteration, hopefully, and that's really important. Iteration goes with consolidation, elsewhere you're going to be accumulating technical debt. And I want this to be agile-like, which means I want this to be low-tech because I have a low budget, and I want to have short turnaround times. So that's the workflow. And something I've seen in science, but also in the industry, is that we're slowly switching from statistics to statistical learning. So statistical learning is machine learning with a statistical flavor. And it's a paradigm shift that's driven by the growing dimensionality of the data, not only in terms of number of samples, but also in terms of number of features. So how many descriptors you have for each sample. And the reason is that sensors, in a general sense, things like a web page is a sensor nowadays. A phone is a sensor. Everything is a sensor. Everything gathers data. So we're all starting to have much, much more data. It's cheap. It's noisy. It's high dimensional. So we're going from this picture of, I've got a bunch of points and I fit a model into it, and then I look at how well the model fits, to one that is more interested in prediction, and prediction from high dimensional problems. So we're looking at needle and haystack problems. All right, so that's the picture. We've got plenty of problems. Let's just make software to solve these problems. So then we're going to have one more problem. So making software, I'm more and more basing it on a simple design philosophy that I've tried to summarize here. First point is, I don't try to solve hard problems. Hard problems are hard. And I try to solve my original problem. And I try to make sure that I'm not solving a problem that's harder than my original problem when solving my original problem. Software needs to be easy to set up and to work out of the box, which means I'm low in dependencies, I want conventions over configuration, default parameters. Elsewhere, I won't have any users. And that includes my students. They will not use my software. Software should fail gracefully, Software fails. That's a fact. But it should try to fail as little as possible, and when it fails, it should be understandable why it fails. That's really important. I think that's one of the major keys of success of Python. For an advanced user, debugging Python is much easier than debugging C. And then last, quality. Software is about quality. If you don't do high quality software, you won't have any users. Therefore, why are you doing software? You might as well, do something else. Final note, don't try to build a big software that's going to solve all the problems. It's not going to work because A, you're going to solve all your problems and not all your neighbor's problems. And B, you're going to be the only one who has the expertise to track this software. And that's really important. You're building yourself a best factor of one. So break down your problems into projects that require different expertise and then try to build software on each of these projects. So, scikit-learn. I'm one of the original core developers of scikit-learn, and I'm somewhat the project head of scikit-learn. So, do you all know about scikit-learn? This is not a tutorial on scikit-learn. I'm assuming that you know basic things about scikit-learn. The vision of the project is to have a machine learning toolbox that can be used by people who are not machine learning experts. When we started, people would tell us, yeah, it's not an interesting problem. We want advanced machine learning toolbox, not simple things. So we want a black box that can be opened. That's why we're in Python. That's why we have objects that are fairly simple that you can open them and combine them. So it's finding the right trade-off between what just works and what's versatile. And you can think Apple versus Linux. And I've seen a bunch of geeks, as they grow old, they start having iPhones and Apple computers. So things just working matter a lot. So we're not going to solve all the problems for you. Remember, I don't solve hard problems. So things like feature engineering, domain-specific cases, we're not going to solve them for you. The good news is that Python is a Turing-complete imperative programming language. So you've got these set of tools, and you can subclass an estimator. You can write your own code, and for me that's very important in the design of scikit-learn. Is that I'm not going to go out of my way to solve every user's problem. Elsewhere, I'm just going to have a complete spaghetti code that is incomprehensible. So we want to cover all the 80% use cases in one single package. That's the goal. So if I try to look back and think, what have we done right in scikit-learn? Well, I think one thing that we've done right is to stick as much as possible to high-level programming. This is what has been keeping us afloat. We have a ridiculous number of contributors. We have huge activity, pull requests and bug reports all the time. The only thing that is preventing us from dying under the load is the fact that we're as high-level as possible. So how do you stay performant and be high-level? Because I think we're reasonably performant. And so the secret sauce is you want to optimize algorithms, not for loop, not low-level optimization. That's really important. You should perfectly know NumPy and SciPy. Perfectly. I'm not kidding. Any significant data should be arrays or memory views. And people are going to tell me, yes, but I've got a bunch of strings and I don't know how to do this. There are ways around this. There are things like the feature hasher in scikit-learn. You just try to find a way to put your data in arrays, continuous blocks of memories, basically. And then avoid memory copies and rely on no-level numerical libraries like BLAS or LabVac. So, oh great, you can't at all see the light gray. So you can't see what the, oh no, it's here. So your tools are, and Ian mentioned it, line profiler and memory profiler to understand this better, and that's one of my own pet projects, but the SciPy lecture notes give you a lot of information on NumPy, SciPy, how to optimize code. And basically, if you know them all, then you're pretty good. Last but not least, we try not to do any compiled code. Sometimes we have to. Then we use Python. We don't use C or C++. A lot of us can code in C or C++, even though I tend to forget. We don't use it. Python is more maintainable. And each time a new contributor comes in, there's a bit of a fight. He's like, yeah, but Python, you know, I know C. We're really happy about this. Really happy in the long term. So just to give you an example, rather than talk abstract, I'm going to talk about the pull request that I've been working on for the last, what, a year and a half? Tells you I'm getting old and I don't have enough time to code. So the idea is that we're going to implement hierarchical clustering. And the core idea is that we're going to loop on taking the two closest clusters, given a certain distance, merge them, and update the distance matrix. So we're building, hierarchically, agglomeratively clusters. So the interesting thing is that this kind of clustering is actually faster when you have constraints, because then you can code a sparse distance matrix. First insight. Second insight is, well, I'm going to keep, taking the minimum of this distance matrix. Maybe I can use a heap queue. Heap queue is a data structure that will keep its minimum always really easily together. You add something to it, and it reorders to have the minimum. So that's one way of avoiding, computing the minimum on the whole data matrix all the time. So that's already a huge gain when you do this. Python has a heap queue module, so you're fine. And then, to keep the neighborhood information, we needed a sparse Grubble structure. So that's tricky. So I thought, hey, skip lists. Skip lists are a probabilistic data structure. They're somewhat in between trees and lists. They're super sexy. They're using things like, I think they're using Reddit. I was like, I want to code a skip list. So I coded a skip list in Python. That was super challenging, pointer arithmetic and memory allocation. And it took me a while. I was super proud. So it's got O log n insert, removal, random access. Great. And then I realized, so that was really tricky code. And then I realized, C++ map construct, that's pretty much what I need. And then I can wrap it in Python with a couple hundred lines of Python code, and gives me pretty much all this. That's an interesting way, interesting story of how we go into super complex things, and then we figure out once we understand our problems, we can do it very, very simply. So all this code, bang, thrown away. So this is how we get super fast hierarchical clustering, and hopefully we're going to merge this soon. All right. Scikit-learn, something I think that's really important from the API design. So I think people kind of like this Scikit-learn API. I'm going to give you a bit the ideas that are behind the Scikit-learn API. And one of the core ideas is that we want to separate data from operations. So if data is this, you've got an agent that walks around the data, and that agent is your operation. So that's the conceptual picture, and if you look a bit, it's present in Bokeh, maybe a bit hidden, but it's present there. It was present in Chaco before. It's quite clearly present in Hadoop, but it's also hidden behind Miami, and it's also in CPUs. CPUs, you've got the cache, and you've got the registries. So it's a fairly generic pattern, even though it's hidden everywhere. It's also hidden in Scikit-learn. So I'm going to show you how it's present in Scikit-learn. And the reason it's hidden is that we really wanted to keep an imperative-like language. Declarative programming, as in I describe the operations I'm going to do, is great from the theory standpoint, but it just doesn't match the way the brain works. So we have a core object API that exposes a small data processing language, and if you probably know it, it's fit, predict, transform, score, partial fit. I may be forgetting things, but not much. This is a core grammar, and we can do a lot of things with this. These objects are instantiated without the data, but with all the parameters. And that's really important. That's what means that they can have a life of their own that's detached from the data. So that was a really critical design decision. And then we've got objects like pipelining or merging to be able to build something richer. So this pattern of objects that are instantiated without the data, but with all the parameters they need, you can think of it as the configuration run pattern that is present in things like traits or Pyre. Pyre was a framework by Mike Agvagsis at the Caltech Center for Advanced Research Computing, and I had a lot of discussion with Michael. And so all these frameworks, whether it's Pyre or traits, they're heavy frameworks. They force you to do things. We've done this by convention. You can write a crappy scikit-learn object that don't respect these conventions. There's nothing in the framework that forces you not to do this. It's just us. When we review your pull request, we're going to tell you now. This is also basically what's known as a query in functional programming. So for those who don't know this, it's basically functional partial. So I'm just taking a function that has parameters and takes data, and I'm just going to partial out all the parameters. Then the function only takes the data. And you can link it remotely to IDs from the MVC pattern. So just to show you that APIs they're not designed out of nowhere, even though they seem simple. All right. How are we going to do big data and small hardware? Because I don't have a budget. I only have small hardware. Well, actually, we're going to do biggish data, not really, really big data, and we're going to use smallish hardware. Although I do have users that really want to use MacBook Air to process their data. I'm not kidding. They really want it. And they're not processing their data now. So what we don't want to use is Hadoop. I'm sorry. I'm not using Hadoop. It's meant for huge data sets, meant for distributed storage, computing clusters. I don't have these problems. I have gigabytes, terabytes nowadays. I want to do Python. That's really important. I don't want my students to have to learn multiple languages and learn debugging and being productive in multiple languages. And I want to use off-the-shelf commodity hardware. That's really important. I think that's 99% of the problems that are covered by this. All right, I still want to be efficient on biggish data. So one important trick is to use what's known as online algorithms. So online algorithms, they process the data one sample at a time. And to give you an example, if I'm asking you to compute the mean of a gazillion numbers, is that hard? No, it's not. I mean, I just do a running mean. Okay, there are going to be difficulties with rounding errors, but running mean is going to be able to take as much data as you want, right? So that's the core idea. You've got an algorithm that converges. In general, it converges only with high probability to expectations of statistical properties of your data, but it's just moving around and eventually converging as it sees more data. The way we implement this is that we use the mini-batch trick, which is that we're going to bunch observations together to be able to have good vectorization. And one example is k-means clustering. So I'm going to apply this on a actually fairly small matrix, which is 10,000 samples and 200 features. And I'm going to compare the SciPy k-means with the scikit-learn mini-batch k-means, and we've kind of tuned the parameters so that they were reasonably comparable. SciPy takes 11 seconds. Scikit-learn takes less than 1 second. Really what makes the difference is that this is a mini-batch algorithm. I could crank up the sample size, and it would get even worse. Just, I hear a lot of people telling me how they need to have distributed array operations on a cluster to be able to add together arrays that have petabytes of data. I'm like, no, I don't need. I can do this. Other important trick, what I call on-the-fly data reduction. Big data, or biggish data, is very often I/O bound. So you're going to want to have something that you can run prior to data analysis or in parallel with your data analysis that reduces your data if you have a lot. Because you're going to optimize things like CPU cache, RAM, you're going to optimize the use of your local disk with regard to distance storage. Also, stupid but true, if you have less data, it's easy to run the algorithms. So the simplest way to do this is to drop data. And for instance, you can, in a loop, take a random fraction of the data and run an algorithm on that fraction. And then you do this several times, and then you aggregate the results across the different subsamplings. As long as the algorithms that you're running are superlinear, on the sample size, this is going to be useful. And the reason this works is that it exploits the fact that you tend to have redundancies across observations. And if you can run this loop in parallel, then you've got a double win. Okay? So in scikit-learn, we've got a bunch of ways of doing fast data reduction, things like random projections or clustering features. If you've got images, this can work fantastically well. Or hashing, so you can turn text into a hash that then is much smaller and also fits in a given memory slot, so then you can work with arrays, use these. And to give you an example of these tricks, it's the randomized SVD. I mean, the randomized SVD, it's just a randomized SVD, so you can apply it like a normal SVD, but inside there's tricks like using random projection-like approach. And so here I've compiled it on, once again, actually not terribly big data set, and I've compared it to my LAPACK solver that takes 6 seconds. The RPAC solver, so that's a power iteration method, asking for the 10 biggest eigenvalues or signal values, that's 2.5 seconds, and the randomized SVD takes 0.3 seconds. And so you're like, okay, but that's an approximate solution, right? So then I'm going to look at the error between LAPACK and RPAC and LAPACK and our solution. Well, our solution is actually epsilon closer to LAPACK than RPAC. So it's a pretty good solution. So randomized data reductions can work pretty well. All right, talking about hardware, we've just bought a new box, 15 kilo euros. That's okay as a budget. It's got 48 cores, almost 400 gigs of RAM, and 70 terabytes of storage, and we designed that storage quite well. But that's not too expensive. And the surprising thing is that we've got access to an 800 CPU cluster, so that's 200 nodes, I believe. And the kind of work that we do gets actually done faster on this 15 kilo euro box on which we've just installed standard Ubuntu than on the cluster that, that's 200 kilo euros, and it requires a system admin and it's dedicated Linux install. It's all about the access patterns, at least in our use case. So that's kind of interesting. And we're not the first people to say this. There's this great paper by Microsoft Research that says nobody has ever been fired for using Hadoop on a cluster. And they show numbers like this. So people come in my office every day saying, oh, I want my code to be efficient on the cluster. Well, think about your problems. All right, moving on. We want to avoid framework code. Parallel computing, storage. I'm going to build a framework that dispatches things. Oh, the problem with this is then it becomes really hard to maintain. Each time you get a new person, you have to train that person on the framework. We really want to avoid framework code. So that's where joblib comes in. And for example, we want to do parallel processing. First thing, I'm only going to worry about embarrassingly parallel for loops. I'm not going to worry about message passing problems, wasted too much time on this. Life is too short to worry about deadlocks. Once again, I'm going to have to keep in mind that what's going to condition the efficiency of my code is probably going to be things like data access, even on one single box, because the memory bus can very, very easily be a bottleneck. So we're going to have to find the right grain for parallelization. If I'm too fine, I'm going to get overhead from it. If I'm too coarse, basically the workers are going to be competing for the data access. So this is joblib parallel. This is all you need to know. 2 imports, and then you write a generator-like expression, and it gets computed in parallel. This is kind of OpenMP style parallelism. So there's nothing more. Right, move on. So first, why are we not using Python, multiprocessing, Celery, MPI, everything? Joblib is at a higher level. It solves a different problem. It solves that problem, right? Not all the problems that the other things are trying to solve. So where's the value? Well, one value is that we have no dependency. We don't even have a dependency on multiprocessing. If you don't have multiprocessing, it won't fail. It just won't do parallel computing. Too bad. Minor details that matter a lot, like we get better tracebacks, debugging matters. That's really so nice. Olivier implemented automatic mem mapping of arrays to be able to share memory between processes. Because if I do parallel computing, chances are, if I've got big data, I'm going to kill my memory rather than killing my CPUs. Something that's really critical is that we've got on-the-fly dispatch of jobs. So if you're iterating over your parallel for loop, you don't want to dispatch all your jobs in the beginning and then get them back. Because you're going to kill your memory if your jobs have memory usage. So that's kind of really tricky to code, actually. The user doesn't see this, but it's really valuable. And this is also new by Olivier, is that we have a threading or process backend. And yesterday, Linda was talking about random forests in scikit-learn. This is so Andy Miller's box that has apparently 32 cores. This is what random forests now look on this box. So 100% CPU usage for everything. It's actually fairly challenging to get there, to use all your CPUs like this. And on top of this, you can't see it because it's really low, but there's just about no memory usage. How did we get there? It's a lock-free Python code and threading backend. And the good thing is, we can switch from multiprocessing to threading backend with only one keyword argument in parallel. So as the code evolves, we have more options. This is new. This is super exciting. How much time do I have?
You've got 12 minutes.
All right, I'm going to skip this. I'm going to talk a bit about caching. Caching is important for reproducibility. I see people when they do data analysis, they just change scripts, and then they remember not to run this one because the data hasn't changed. I see this all the time, where they comment outlines. This is ridiculously non-reproducible, and it's actually a problem because when you get new data, you can't run your analysis. You've got to manually do operations. It's also very important for performance. When you think about it, not computing something that you've already computed is just the crux of every optimization. And it's there everywhere. It's there in CPU pipelines. It's there in web applications. So we're going to want caching. OK, so that's easy. There's the memorize pattern. You can find it on the Python cookbook. So we're just, I'm sorry, this is a bit low. We're just going to create a memory object. And it has persistence to disk. So we're going to give it a path. And then we can use it to decorate a function. Function f, I'm going to decorate it into function g. And then the first time I call function f on some object, it computes something. The second time I call function, it doesn't. It's just retrieved. So that's trivial. Now the difficulty is getting it right. And we're doing biggish data. So A and B can be pretty big. So I want this to work well with A and B big, and C could be big too. From a design perspective, I want this to work all the time. Therefore, A and B can be arbitrary Python objects. No control on what you're putting in. And on top of this, I don't want any dependencies because that's how I work. Something new, I've actually discovered that it wasn't merged in while doing this presentation, so we need to merge it in. This is giving us the Lego bricks for out-of-core computing. So we now have a call and shelf method on the decorated function that will call the object, call the function, and not return the result, because the result might take a lot of memory. So it just stores it to disk. And later, I just can call the get method on this guy. So then I can do parallel computing, and I'm only returning these memorized results, and then I'm loading them as I need them. So we're starting to use it to process some pretty big data in my lab. And that's really, really simple pattern. You're almost not changing your code. The only thing is, you've got to write functions. People don't write functions. My students don't like to write functions. Well, it's the basic abstraction of reusable code. So it's a good thing. I'm forcing you to write functions. I will not make a context manager for joblib. With memorize, this will not happen. So how do we get this working? Well, we're going to be computing an MD5 of so an MD5 hash of the input argument. Why MD5? Because it's in the Python standard library, not because we like it. So why a hash? Well, hashes they're nasty because they're super black boxy. I can't look at a hash and know the input argument. The thing is, they're completely generic and super robust. If you don't get hash collisions, which don't really happen, you can just use it as a black box and it will always work. So people keep telling me that they want something else than an MD5 hash in there. I'm like, sure, but I want something as robust. Now, making it work is the challenge, and this is kind of a nice engineering part. So we want to take an MD5 hash of an arbitrary object. So we're going to create an MD5 hash object. So it's something you just give it data strings or buffers, and it hashes them. And then we're going to subclass the pickler from the standard library. And that thing is a state machine that walks the object graph. That's just the way it is. Look at the code. It's brilliant. And then we're going to walk, using this subclass, we're going to walk the object graph and then feed all these objects to our MD5 object. Little detail is that when we find something that is a memory view or an ND array, we're not going to convert it to a string to pass it to the MD5 algorithm. We're going to simply give it the pointer to the data. So that's what makes it efficient. That's actually fairly efficient. You'd be surprised. Similar, we want to persist arbitrary object, and instead of using pickle, we're going to subclass the pickle and persist differently and fast things that are memory views or NumPy arrays, and pickle the rest. So we get multiple files, but the thing is we're storing structured data as structured data in an efficient way. With parallel computing and the cache store, we might run into concurrency issues. So I tried going the database way, and that didn't work. Because I did it wrong, but also because databases are, well, it's tricky to use them right with big arrays, let's say. It's not impossible, but it's tricky. So the way we're doing this is that we're relying on atomic POSIX operations, so file system operations, and if they fail, we just, recompute, whatever. It's got really good performance, read and write, and it's usable on shared disks, so say clusters. We want to make it fast, so how do we make it fast? Well, we might be able to use compression. I had this really interesting experiment where I was processing data files, and then so I could zip them or not zip them. And when I was doing this on one core, it was faster not to zip the data file. When I was doing this on my 12 cores, it was faster to zip the data file because the disk was the limiting factor, not the CPU, and it was significantly faster. So compression is definitely the way to go. We're using zlib, not anything fancy, once again, because it's in the standard library. So people, BLASK people provide us with a great package, well-tested compressor, and we might optionally use it. Tricks are we need to use, on top of this, we need to use the compressor in an online way to avoid, blowing up memory. So we avoid copies by passing in directly the buffers. And also, one trick is that we separate, so we don't say transpose arrays to make them C-ordered. We pass the raw buffer and we store the strides and information. That avoids a copy. And one thing that we're starting to have is that when you're in a cluster and you've got 800 CPUs hitting on a single storage, something as simple as opening a file gets really, really slow because you're triggering locks in your file system. So we're starting to realize that actually we need a single file dump, not multiple file dumps. So we're revisiting this code. The challenge is it has to be done in a streaming way to avoid, blowing up the memory usage. So taking a step back, what matters with I/O on really large systems? The number of bytes stored, so that's where compression kicks in. If you're exchanging too many bytes, you're going to bring your network or your SATA bus down. The memory usage, if say when you're storing or when you're unstoring, you use too much memory, then your computing nodes are going to come down because they're going to run out of memory. And that's recent because we're scaling up the number of atomic file access. And we're really bringing our cluster down. I'm not kidding. We're bringing a cluster down with I/O, locking it. Like an analyst takes 5 minutes. So when you scale up, this matters. The way out of this is to have real distributed storage. And no, we're actually bringing our distributed storage down. So it would be things like not using POSIX API, so basically, Hadoop file system or whatever NoSQL database, but we don't want to go down that way. Some small benches, I'm not going to go into the details, but basically this is to tell you that we're pretty much as fast as PyTables, which uses a really cool compressor because we've avoided memory copies and we're a bit careful with what we do. All right. I said we wanted to build an ecosystem. So it's not about building a program, building a script. It's about helping your future self that's going to come back in 5 years and find that your code has grown. So something that's extremely important is to build a community. And so if you look at scikit-learn, we've got a huge feature set. This is the project growth over the years, and it's exponential with plateaus. We have more than 200 contributors, probably around 300 by now. I think 12 of these people are core contributors. By core contributors, I mean they have common access, but they use it on a daily basis, not on a daily basis, weekly basis. From the start, I would like to stress that we've always had a full-time INRIA programmer on this. I'm just stressing this because INRIA we've got all our grant application have been rejected, and INRIA has been taking on its own money to fund this. I don't make these decisions. Higher up make this decision. So estimated cost of development with a really standard model is $6 million. It's huge. Why do we do this? Well, because code maintenance is expensive. My mailbox is a disaster. Look at that. 53,000 unread email. And then going through my email, I find this. So this is a guy writing a private email saying, look, I can't use your software. Can't you reply to my email? I get this all the time. So why do we share software? Why do we try to have a community? Because our benefits only come from a tiny fraction of that code. Data loading, do we care about data loading? No, we're not going to make our bucks on data loading. Standard algorithms, no, we want them to be available. So we're going to share all the common code and keep our precious secrets. Elsewhere, we're going to die under code. Thing is, those secrets will become less precious with time. So somebody might come up and code features, and for instance, in my group, we don't do random forests. But it happens that the Belgian guys really like random forests. And so Gilles has come up and contributed this, and then many people have worked with him. And this is a tweet by Gilles that shows across the different releases of scikit-learn how random forests have gotten much, much faster. I didn't have anything to do with this. This is fantastic. When I need random forests, they're fast, thanks to other people. And they even do the figures for my keynotes, for me. Awesome. All right, really quickly, you want to build a community-driven project, you're going to have to think about it. You're going to think about your users, what docs and examples, use GitHub. Don't use anything else. Really important, limit the technicality of your code base. Elsewhere, you're going to be the only one coding in it. And really focus on your contributors. Give them credit. They're the people doing this. I think we're doing something right. And this is a graph that shows you the number of commits in different projects for each contributor where the contributor number doesn't mean anything. So what we're seeing is that scikit-learn, and this is normalized. There's no absolute value. What we're seeing is that the relative importance of the committers in scikit-learn is pretty good. We're falling down really slowly. We have many people who contribute a lot. And if you look at other projects, well, some of them are in big trouble. One of them that's in big trouble, where is it? This guy, my Abby, my unloved child. So probably I did a few things wrong, and one of them is the code base is too technical, and another one is it took us ages to go to GitHub. we didn't brand it right. You know, we're getting exactly what we put in. Tragedy of the commons. You know this. It's the idea that each individual is, by being rational, not acting in the community's interest. And I think we're seeing it because once we've making things boring, people move on to something else. I'm going to finish. And so core projects are taken for granted. I think scikit-learn were really good, but non-Py contributors, SciPy contributors, nobody contributes to NumPy and SciPy. You should look at the number of people working on it. Everybody uses it. So if you're not contributing to these projects, at least remember, we need citations. We need, in papers, cite us. On corporate web pages, tell that we're important because we're not even getting funding. We're not getting funding. People are telling us, you're not exciting, you're not important. All right, I'm going to finish. Important messages, the 80-20 rules solve only the important problems. They're going to take 20% of your time compared to solving. You're never going to solve all the problems. To wrap up, how do you build a great environment on a budget? You set the goals right. You don't solve hard problems. You use the simplest technological solutions possible. That actually requires you to be very technically savvy and not to use this sophistication. It took me a while to realize this. You focus on the human factors, both in your user base but also in your developer base. If your developers are happy, they're going to be productive. That's pretty basic, but it's really important. It really matters. It took me a while to realize this. And just to give you an example of perfect design, that's a Tetra Pak. It's a piece of paper that contains milk. It solves only the problem it was designed to solve, nothing else. It's even got a lid for the human factor so that you can open it. That's perfect design. So you want to aim for this, as simplest as possible, just works. Thank you.
Thank you, Gael, for the keynote. We have time for 2 quick questions. Do we have 2 quick questions? Can you shout?
You said early on that your code base for this is almost all Python, but in GitHub it says like 80% is C. How does that work?
We are checking in Python-generated code for good reasons. People might disagree, and Python generates a lot of C code.
Do we have one more question? One more question, Philip.
I find that there's no difference between organization and normal users. I think there is a fraction, small, finite, of people who use your software who are going to contribute back. It's tiny. So the only way you can get more contributors is to get more users. Now, where you have to make your choice right is that if you're going to develop an end-user application that's all clicky and everything, you're not going to get contributors for this. That's why I'm no longer doing graphical user interfaces. Sorry, people. So unfortunately, unless mentality is completely changed, some problems will never get solved. But the way I go about this is I try to not dumb down too much problems so that my users might become contributors and then have as many users as possible. This has worked. Everything else has failed.
Okay, we're going to take 5 minutes, and then we're going to start up again with James in here talking on generators. Remember that Peter's talk has been cancelled, so it'll just be James talking in here. And later this afternoon, Gilles and Peter will be talking on scikit-learn if you're interested to learn more about some of this. Let's just thank Gael again, and then we'll take a break.